Now we look at something called Norton's theorem. Applying Norton's theorem then will simplify a circuit just like we did with the Thevenins, describe the form, obtain the equivalent current source, and obtain the equivalent resistance. So what we're going to see is where a Thevenins dealt with using voltage sources, the Norton's theorem, Norton's equivalent, deals with current sources. So just like we saw in the Thevenins, this is the equivalent Norton's theorem circuit when we do a Norton's exercise, if you will, circuit reduction using the Norton's theory. The process is a lot like the Thevenins. If this is our original circuit and we've got some load attached between A and B, with the Norton's equivalent, what we're going to do is we're going to short the ports A and B together. In essence, we're going to remove the load, short the output, and then do our analysis pretty much like we did it before. So in this case, if we want to determine I Norton's for this circuit, for the area within the beige part, again, the first thing we're going to do is remove the load and short the circuit out across the output. So in doing the analysis then, we short the terminals between A and B. The Norton equivalent circuit current then through the short is where the Norton's current flows. First, the total resistance seen by the voltage source then is, okay, so again, you can see what's going to happen here. R2 and R3 are going to be now in parallel in series with R1, and our current will flow then through that section. So the total resistance then becomes R1 plus R2 times R3, product over the sum, R2 plus R3. And we get 47 ohms plus the product over the sum gives us 79 ohms of resistance for our total resistance in our Norton's reduction here. The total current then from the source is, just like before, V source over R total. So 5 volts by 79 ohms gives us a total current then of 63.3 milliamps for our current from V sub S. So now if we apply the current divider formula for I Norton, the current then through the short, I Norton then is equal to R2, because we're going to take the current through R2 and divide it by R2 plus R3 times the total current, gives us 47 ohms by 147 times 63.3, and we get 20.2 milliamps of current then as I Norton. So that will be our Norton's current. This is the value of the equivalent Norton current. So now we want to find R Norton, just like we did with R Thevenin. Find R Norton for the circuit within the beige area. Again, first reduce V sub S to 0. How do we do it? Well, we take the battery out and short across the poles. So looking in at the terminals A and B again, so we're going to be looking into the output port, you can see that the parallel combination of R1 and R2 is in series with R3. Thus, the Norton's resistance is R3 plus 1 R1 divided by 2. Again, these guys are both the same value here. So the 100 ohms plus 47 by 2 gives us 124 ohms as our R Norton value. So if we draw the completed Norton equivalent circuit for the original circuit, then you can see we have I Norton 20.2 milliamps, R Norton 124 ohms. So what are the two components then of a Norton's equivalent circuit? Well, that's I Norton and R Norton. That should be not R. R Norton. Okay. Next. Draw the general form of a Norton equivalent circuit, just as we saw before. There is I Norton current source. There is R Norton internal resistance. So in this case, they want us to find the Norton circuit as seen by R sub L. So for this one, I'm going to let you solve that. Go back and look at the process and determine how we get to 515 milliamps and 9.7 ohms to check your work. So in the next section, we're going to look at something called maximum power transfer theorem. In this case, we want to make sure that we have our load matched properly and that we get the maximum power on the output. This is very important for things like in audio systems where you want all of the power delivered to the speakers so that you're not losing anything or overdriving and getting distortion.